Welcome to class, everyone. Today, we're diving straight into the foundational biomechanics and motion mechanics that govern absolutely every single movement your incredible body makes. Whether you're throwing a baseball, rehabbing an injury, or honestly, just sitting in your chair listening to me right now, there is an entire fascinating world of physics happening right beneath your skin. I am so excited to guide you through this explainer because I promise you, once you actually understand these roles, you'll literally never look at human movement the same way again. Here's our roadmap for today. We're going to cover the language of movement, mapping the human body, the laws of motion, gravity and body control, finding your balance, and finally, the mechanics of force. Let's get right into it.
Section 1. The language of movement.
So, to kick things off, let's talk about biomechanics. This is basically the overarching science where your anatomy directly meets physics. It's the comprehensive study of both the internal forces, like your muscles contracting, and the external forces, like gravity or pushing a heavy weight that acts on your body. It looks really closely at the real-world effects produced by all of these forces working together in harmony.
Next up, we have kinetics. Now, kinetics cares about the why of movement. It specifically analyzes those invisible forces that cause your body to initiate, stop, or change its motion. Mathematically, it's defined by that classic equation we all remember, force equals mass times acceleration. Basically, if you want to know exactly why a movement started or stopped, you look at kinetics. On the flip side of that, we've got kinematics. In stark contrast to kinetics, kinematics is just about observing the pure movement itself. It completely ignores the forces causing the motion. Think of it like watching a video of a skeleton moving, but on mute. You're simply looking at the angle of an elbow changing or how a bone travels through space, without factoring in the pull of the bicep or the actual weight of the arm. Let's actually apply this vocabulary practically, say, to everyday exercise. In an open kinetic chain movement, your distal segment, like your foot or your hand, is totally free to move in space. It's usually non-weight bearing, kind of like when you're doing a seated leg extension at the gym. But in a closed kinetic chain, that distal segment is fixed against a surface, like your foot planted firmly on the floor during a heavy squat. So ask yourself right now, when you walk up a flight of stairs, which chain are you utilizing? Trick question. It's actually a dynamic mix of both. Moving right along to section 2, mapping the human body. I want you to literally visualize these anatomical planes slicing right through your body at this very moment. The sagittal plane divides you into left and right sides, which is where flexion and extension movements happen. Then the frontal plane divides you into front and back halves, dictating abduction and adduction. Think doing a jumping jack. And finally, the transverse plane cuts you into top and bottom halves, which is where all of your rotational movements occur. Every single movement you make happens within one of these planes, pivoting right around its corresponding axis.
All right, section 3, the laws of motion.
Okay, so the big takeaway here is that a body at rest genuinely wants to stay at rest, and a moving body wants to keep on moving. That's inertia for you. Overcoming this inertia requires significant force, which is exactly why a patient with weak muscles cannot produce or control movement effectively without some sort of mechanical assistance. Their muscles simply can't generate the force required to break that inertia. Motion only results when force is applied, and the momentum of that motion is simply your mass multiplied by your velocity. Which brings us to section 4, gravity and body control. Gravity. It acts continuously on us, constantly pulling our mass toward the center of the earth. But where does that pull actually concentrate? It happens at your center of gravity. This is the exact point where your body's mass is perfectly equally distributed. In a standing adult, this point sits right anterior to your second sacral vertebra, which actually, fascinatingly enough, happens to be at exactly 55% of your total body height. But just knowing where your center of gravity isn't quite enough. To keep you from falling face first onto the floor, there's this invisible plumb line dropping straight down from that center point, and we call it the line of gravity. For you to maintain postural equilibrium, this line absolutely must land squarely within your base of support, which is the physical area beneath you that's supporting your body. If that line falls outside your base of support, gravity wins, and down you go. Section 5, finding your balance. So equilibrium is what happens when all those forces acting upon your body are perfectly balanced. If you're lying flat on the floor right now, you're in stable equilibrium because you have a massive base of support and a very low center of gravity. But if you stand up on one foot, suddenly you're in unstable equilibrium. Your center of gravity is high, your base of support is tiny, and any small displacement or sway dramatically magnifies the forces acting against you, pulling you right off balance. And maintaining that balance? It is definitely not just a simple physics or math problem. It requires a rapid-fire symphony happening inside your body. It relies on biomechanical positioning, like how wide your stance is. It simultaneously requires constant sensory input from your eyes, the vestibular system in your inner ear, and proprioception. And finally, it demands musculoskeletal reactions. You need the actual physical muscle strength and coordination to quickly adjust your hips or ankles to correct your posture the split second you start to sway.
And finally, Section 6, the mechanics of force.
All right, force alters a body's state of rest. When you apply that force over a distance, you're doing work. And this brilliantly illustrates how your body's energy systems actually function. Every single time your muscles and tendons stretch, they store elastic energy like a tightly coiled spring, giving you the capacity to do work. When they recoil, they produce power, which is the rate of performing that work, all while fighting against friction, which is the persistent force opposing motion when surfaces slide against one another. But here's a really fascinating question to consider. What happens when you've got multiple muscle fibers pulling on a single bone from slightly different angles, all at the exact same time? How does your body calculate where the bone should actually move? Well, it uses what we call the parallelogram of forces. This is basically a mathematical method of compounding two separate forces acting at an angle to find their ultimate combined path. A perfect everyday example of this in human anatomy is your deltoid muscle. Different fibers of the deltoid pull at slightly different angles. By combining these angled pulls, the body creates a single powerful resultant force represented by the diagonal of the parallelogram that seamlessly lifts your arm upward. It's just pure, elegant physics happening right there inside your shoulder. As we wrap up today's explainer, I want you to do a quick posture check and mentally map these physics onto your own body right now. What invisible forces are acting on you in this exact moment? Are your feet forming a closed kinetic chain on the floor? Where exactly is your line of gravity falling? Take a second to ask yourself how your incredible musculoskeletal system is effortlessly managing all of these complex mechanics in real time just to keep you sitting upright. It is a brilliant, continuous masterclass in physics. Thanks so much for joining me in class today, students. Stay curious and keep learning.